Hello everyone, today we're going to look at chapter 19.6, Analysing Starlight, and with that we'll be looking at the use of a transmission diffraction grating to determine the wavelength of light and using an equation d sine theta equals n lambda so that we can find out different values of wavelength depending on the grating spacing. So let's get started. If we remind ourselves of what we mean by a diffraction grating, all we mean is something like cell bars. So something that's got lots and lots of slits in so that when light approaches, some of it gets blocked by the bars and some of it is able to get through and get diffracted as it passes out of the other side. You would have seen this topic briefly before and certainly looked at young double slit, and the difference is young double slit, clues in the name, there's two slits, whereas with diffraction gratings in this topic there are multiple slits. So the fringes produced by passing light through a double slit aren't very sharp, so it can be quite difficult to determine the position of the centre of each maximum, so that's where we have the colour. So to overcome this, what we do is we have a diffraction grating that has many slits, so potentially thousands across a plastic slide. And generally speaking, we would say a value might be 1,000 lines per or inner millimetre. So quite a few. And then by using a large number of lines, we then get a far brighter interference pattern. Moving on to the specification points. So, transmission diffraction grating used to determine the wavelength of light, and then there's that equation. Note that proof of the equation is not required, even though it's quite nice actually to have a little look at. So diffraction grating has a regularly spaced slit or lines that diffract and split light into beams of different colour, travelling in different directions. So as I've said, using a large number of gratings produces a clearer interference pattern, so that's why maybe it makes it slightly better than the young double slit. But you have last seen that where you saw a different equation. Now I believe you saw the d sine theta equals n lambda when you looked at young double slit, but we'll certainly be looking at that in a bit more detail shortly. So just as previously, the formation of maxima at a particular point depends on the path difference and the phase difference of the waves from all slits. If we just zoom in on one part, we've got obviously a gap there and a gap there, and that gap is then repeated many times as you get further away from that area. So we've got a value of D, and the value of D is the distance between the two slits. And we've got monochromatic light coming in, so if you remind yourself of what that means, it's just wavelengths of light of the same number, so it's one colour. Then as it approaches, light will pass through and it will diffract, and that will eventually meet at a screen, and that's where you get a region of constructive and destructive interference, where you get your maxima, your bright lights, and your minima, your dark shadows on that screen, depending on that path difference that it's travelled when it eventually meets, whether it's in phase maxima or out of phase cancellation and minima. And as it says just here, when you have a whole wavelength difference or path difference, that's when you get a maxima. Another final thing to mention before we move on is where the angle is measured from. And you've always got a normal, and we always measure the angle from the normal. When the light passes through, you'll then get a series of different orders. The one in the middle we would call n equals 0, so that's the 0 order maximum. And then n equals 1, n equals 2, and that gets repeated on both sides. But as a reminder, theta is always measured at the normal. So the angle for n equals 2 would be all the way down there. In your book, it does go through the proof, even though proof is not required of the d sine theta equals n lambda equation. But we've got here my version, where we've got sine theta is opposite over hypotenuse, where opposite is AC and the hypotenuse is AB. What we've got then is this line here that's at right angles to the AC line. So the distance AC is the extra distance travelled by this bit of light compared to this bit of light to a distant screen. And we know that the distance AC has to be a number of wavelengths for it to be in phase, because for it to be in phase you've got to have a whole number of wavelengths path difference. And then our hypotenuse is just the distance just here between the slits, which we have labelled D. Then if we rearrange it, we can get d sine theta equals n lambda. And that is different to Young double slit equation, so always be aware what topic you're answering a question about. So if you want any more information, there is a bit more in the book about this, but equally no proof is required, although it is quite a nice one to have a little look at and try to understand. I found an example here for us to look at, and let's just start with it from about halfway down. So this close-up diagram of part of the grating shows that the first order maximum occurs when the path difference between each wave and the next is lambda. So for each triangle, sine theta equals lambda over d, or d sine theta equals lambda. The second order maximum will occur when the path difference is 2 lambda, and the nth when it's n lambda. So the general equation for any order is d sine theta equals n lambda. So onto the question. Light with wavelength 650 nanometers, so times 10 to the minus 9, is shone on a grating with 700 lines per millimetre. How many orders are seen, and what is the angle of the highest order? So to find the spacing D, because it's 700 lines per millimetre, you need to do 1 millimetre divided by 700. And that tells you the gap between each grating. So that gives us 1.43 times 10 to the minus 6. So that's the first skill that you'll be expected to do, is transfer, whether it's 1,000 lines per millimetre, 500 lines per millimetre, as it's given up there, or in this case 700 per millimetre. You need to find the distance between each grating. So 1 millimetre divided by 700 turns out to be a distance of 1.43 times 10 to the minus 6 metres. So depending on how you want to do it, some people prefer to turn the 1 millimetre straight into metres first of all, so that would just be 1 over 1,000 divided by 700, and that would then turn into times 10 to the minus 6 automatically. For the next part of the question, when we want to find n, the highest number of orders, it's worthwhile just looking back at our diagram. So we mentioned earlier that the first order is either side of the 0 order, n equals 2 either side, n equals 3, and it's going to get to a point where you can no longer get maybe a 4th, a 5th, a 6th, 7th order, because it will start going behind the screen. The maximum that you can get ever is where n travels along the grating. And if we measured the angle for that, the maximum angle we could ever get would be 90 degrees. Let's refer back to our equation for a second, where d sine theta equals n lambda. If we say that the maximum angle that you can get to is 90 degrees, sine 90 equals 1. So let's change sine 90 or sine theta and just have that as 1. So d equals n lambda for our maximum number of orders. So therefore, if we wanted to find n, all we need to know is d divided by lambda. Now, we need a whole number of orders. You can't get an order of 2.3 or 3.192. You need a whole integer number of orders. So if the value of n that you calculate turns out to be, let's say, 3.2, then the maximum number of orders that you can have is 3. Likewise, if it was 4.9, well, you've not yet made it to 5, but you have made it to 4, so you have to round down to the nearest integer. So if your answer came out as 4.9, the maximum number of n's, or the maximum number of orders, would be 4. So now let's just go back to our question. I personally do it in a slightly different way to how they've done their example just here. So in the same method just here, I would say to find the maximum number, sine 90 is 1. So n equals d over lambda. We said d was 1.43 times 10 to the minus 6, and lambda is 650 times 10 to the minus 9, which gives us a value of 2.2. And because we always round down, the maximum number of orders, or the highest number of orders, would be 2, which is what they do get to, but I think theirs is slightly more complicated because they don't get rid of the sine theta straight away. Then on to the final part to find the angle, theta. It's just a case of plugging in the numbers again and getting theta out. So d sine theta equals n lambda. So then sine theta is n lambda over d. And then theta is sine to the minus 1 of n lambda over d. So we can put in the numbers. So we know n was 2, lambda 650 nanometers, and then the distance was 1.43 times 10 to the minus 6, which gives us an angle of 65.4 degrees. So what I'd like you to do now is have a go at the 2 practice questions that are here, and press pause, and then when you're ready, press play again, and then we'll go through both of the answers. So press pause, have a go, and then we'll go through the answers. Okay, first things first, we need to find out what the value of little d is. So we would do 1 over 1,000 divided by 550, and that will tell us the value of d. So I'll just put that into a calculator. 1 over 1,000 divided by 550. .82 times 10 to the minus 6 meters. Probably worthwhile writing down the equation at this point. D sine theta equals n lambda. We now have a value for d. We know that the angle is 19, and the first order, so that's n equals 1. So we can rearrange for the wavelength. So 1.82 times 10 to the minus 6 multiplied by sine 19, making sure our calculator's in degrees, and then divide by 1. So that works out for a wavelength of 5.9 times 10 to the minus 7 meters. Now, wavelength tends to be in nanometers for this topic, so you're looking at an answer of 590 nanometers, which sounds about right. And question 2 or question 4. Light with a wavelength of 710 nanometers is shone on a grating with 1 times 10 to the 3 lines per millimeter. What angle is the first order maximum? So n equals 1. We know the wavelength. We know that we need to find d, so again we can do that. So 1 over 1,000 and then divided by 1 times 10 to the 3. Let's just keep it simple rather than converting now. So we're trying to find the angle this time, but let's start with the equation. Always write it down in full. So d sine theta equals n lambda, then sine theta equals n lambda over d. So n, we said, was 1. Lambda, 710 nanometers, so times 10 to the minus 9. Divide that through by 1 times 10 to the minus 6, which equals 0.71, but we need to remember that that still equals sine theta, so we need to inverse that. So sine to the minus 1 of that gives us an angle of about 45.2 degrees. Although given that that's to 2 significant figures and that's to 2 significant figures, 45 degrees will be absolutely fine. In your book it has this picture, and it's a case of understanding why, when white light travels through a grating, that red gets separated from the purple. Let's just remind ourselves of the equation of this topic, which is, of course, d sine theta equals n lambda. Well, let's just focus on one part of it so we can get rid of n, because it could be any of them. And we know that the distance between each of the slits is a constant. So what we can really say is sine theta is proportional to lambda. Just in case anyone has forgotten about the electromagnetic spectrum, one starts at gamma, and then it moves through to X-ray, etc. But let's focus on visible. So at this end of visible, we've got ultraviolet, so that's our purple, our violet colour. And equally at this end, we've got infrared, so we've got our red colour. At the same time, let's focus on the extremities. So gamma, we've got our short wavelengths, and radio waves, we've got our high wavelengths. So in other words, violet has a shorter wavelength and red has a higher wavelength. If we're now saying that sine theta is directly proportional to lambda, let's focus on the red. So where you have a larger wavelength, you'd expect the angle to be greater, so it's more spread out from our normal. Likewise, violet has a smaller wavelength, So the angle when it passes through, because they're directly proportional, will also be less, and that's why you see the violet colour that hasn't spread out quite as far as the red. The angle taken from the normal is less. So we've now come to the end of the video. Have a go please at the summary questions. Answers are in the back, but as ever, please let me know if you need any help with going through them.